If you're curious, I wanted to show you how you could add some more realistic complexity to this simple work model, where there's a certain quantity of work to be done and a number of people dividing the work, and each of the people works at a constant and equal rate. So there's two different things I want to show you. One person on the quiz was interested in the idea that as you add more people, everybody looks at everybody else working and thinks, I'm going to work a little less hard. So like each additional worker is going to make everybody else slow down their rate. So how would you model that? And then a different aspect would be maybe you don't work at a constant rate. Maybe you experience fatigue over time. So the rate at which you work slows down as the time you work gets longer. So how would you incorporate those kinds of ideas into this model? So let's start with the first one, where the rate at which people work are a function of the number of people. So instead of R being a constant, what we're really saying is now R is a function of the number of people. And R still is the rate at which each individual person works. It's just that as the number of people grows, the rate at which each individual works is going to be slightly less. So as usual, I like to imagine things using a graph. So if this phenomenon weren't happening, if everybody worked at the same rate regardless of how many people were in the group, then you'd have like whatever the initial rate was, and this would be constant. The number of people wouldn't affect the rate that each individual works at. But what we're claiming is that maybe it's something like this. Maybe it's linear. Maybe it's some other function. So like, let's think what would make sense. To me, it makes sense that with each additional person, maybe I'm going to work 10% less hard. So I'm just going to ease up a little bit relative to how much I'm already working. So in that case, you could imagine like a data table where this is the number of people and this is my work rate. So if it's just me, I'm working at some initial rate, R sub I. If it's two people, I'm working at 90% my original rate. If I add another person, so this is like times 90%. If there's like a third person, now I'm going to work 10% less hard. So I'm going to take my rate that I was working at with two people and multiply it by 90%. So that would be 0.9 squared times R sub I. So in general, if I wanted to model this for n people, my rate is going to be my initial rate times 90% to the power of n minus 1. And if you think about how that makes sense, like when n is 1, I don't want to change Ri at all. So when n is 1, 1 minus 1 is 0, and so this term doesn't affect it at all. But then with each additional person, I'm multiplying by 9/10 another time. So this is an exponential decay model for the work rate of each individual person as a function of the number of people. So now if I want to kind of plug that sub-model back into my original model, now I've got that the total work time equals the total quantity of work there is to do, the surface area, times the number of people, then times the work rate of each person, but that is a function of the number of people, like this. So let's look at what that looks like in Desmos. So here's what it ends up looking like. I've restricted the domain to be greater than or equal to one person. So with one person, and so like I just made up some constants here. So I'm imagining the total amount of work to be done is 100 units of work, and the rate at which each person initially starts working, is 10 units per unit time. So that means with one person working, it's going to take 10 units of time. As I add more people, they're dividing the work up amongst themselves, so the amount of time drops dramatically. But then once I hit a certain amount of people, adding more and more people is dramatically decreasing the speed at which everybody works. And so the time actually ends up going back up. So this particular model is predicting that with more than 35 people, it's actually going to take longer than with just one person. Is that realistic? I think it depends on the particular context that we're thinking about. But it is what this particular way of accounting for like decrease in work rate actually predicts. Okay, so let's look at, let's not look at how people's work is affected by number of people. Let's instead look at a decrease in productivity over time because of fatigue. So let me make a quick observation here. This is really the same structure as distance equals speed times time. Let's think about surface area as just the amount of work to be done. And let's think about this down here, n times r, as the overall rate of work for the entire group. So r sub g is going to be the number of people times the rate at which each person works. But I'm going to think about all of the collected work as being like the overall rate of the group. So if I multiply this, you end up getting a equals r sub g times time, which is really just distance equals rate times time. It's amount of work to do equals rate of doing it times total time we did it for. So you see that like these models are really the same. Okay, so like where does this kind of idea come from? You could think about it this way. You could think about a graph where this is the work rate of the group, and this is time. So the work rate of the group, let's say, is in square feet per hour, okay? Or let's call it square feet per minute. So, and then time here would be in minutes. So it's like after 1 minute, how much got painted? Well, if the work rate is like 10 square feet per minute, then 10 square feet per minute times 1 minute would mean 10 square feet. But what I want to point out is like the unit canceling that you're thinking of here, so like 10 square feet per 1 minute times 1 minute of work, like you're multiplying so that you can get those units to cancel so that you'll have just the total amount of work that got done in that time. If you think about a different interpretation for that multiplication, I'm multiplying like this length by this height, which is telling me area. So you can think about it this way. The area of this rectangle is telling me how much work got done in that amount of time. And so if it's t minutes, same thing. I'm going to multiply the rate at which work is getting done, the 10 square feet per minute, times t minutes, and that's like giving me the area under this entire rectangle. So this area now is equal to A. Okay, so what happens if the group experiences fatigue over time? Instead of the graph looking like this, it would maybe look something like this. The group starts out collectively doing 10 square feet per minute, but over time, the productivity is going to like linearly decrease, let's say. So let's say this is after 10 minutes. The group is the group tires quickly. So what I want to emphasize is it's the same idea. If I want to know how much total work got done, it's like in 1 minute, the group didn't quite get 10 square feet, because that would be true only if the group continued to work at the same rate. But instead, the group is slowly decreasing in their work rate. So how much work they actually did is the area under this curve with the sloped line. So over 10 minutes, the amount of work they did is going to be this area. So what I'm introducing you to now is like a really important idea in calculus. The idea that the total amount of work done is the rate times the time, but instead of the rate being constant, the rate is a function that can change. So like you can use basic geometry to figure out the area under this curve, but what if we decided that a linear decrease in our productivity is not realistic? What if we decided it was going to be like an exponential decrease approaching some like minimum productivity threshold? In that case, you would be trying to figure out the area under this curve, where this is like an exponential decay function. How would you figure out the area under this thing? Well, that's what calculus provides tools to do. So let's not actually do that until next year when you do calculus. Let's actually look and see what it would look like to work out this version of the problem the rest of the way. So I just said that the area under this curve equals the total amount of work done. So the total amount of work to do in my problem is a constant, it's A, and I want to know how much time is required to do that amount of work. So it's like as we imagine extending this line further and further and further, at a certain point, the area is going to get bigger and bigger and bigger, and at a certain point, the area under the curve is going to equal the amount of work that needed to be done, and that's the time at which we've done all the work. So let's like set up an equation that describes all of these things, and then we can solve for the time that for which the area under the curve equals the amount of work we need to do. I think a nice way of calculating the area is going to be the area of this entire rectangle minus the area of this red triangle. So the area, well, so instead of 10, let's call this the initial work rate of the group. So the area of this entire rectangle would be r sub I times t. But then I want to subtract the area of this triangle. So to figure out the area of the triangle, we need more information about the line. So let's call m the slope of the line. And you know that slope is defined as delta y over delta x. Here the here the x-axis is actually our time axis. So I'm going to rewrite this as delta t. So if I want to find the area of the triangle, I could do 1/2 base times height. So 1/2, and then the base is just this t. But then how do I figure out what that height is? Well, it's given to us by the slope, because the slope equals this change in y divided by this change in t. So if I just want to find the change in y, all I have to do is multiply the slope by the change in time, and I've got that change in y. So here I've got slope was m times the change in time, which is just t. So that's going to add another t there. So now I have this equation, which is describing the area under the curve here, the area under the blue. And so I want to know, when is that equal to A, the total amount of work needing doing? Okay, so now I've got an equation that describes the relationship between all the different quantities. What do I actually want to know? I want to solve for this t. I want to solve for what does the time need to be in order for this quantity on this side to equal the area. So if I rewrite this in standard form, I've got a quadratic equation in the variable t. So if you think about the coefficients, this is the a coefficient, this is the b coefficient, and this is the c coefficient. If I had like a t squared minus bt plus c. So if you want to, you could use the quadratic formula. So I know t is going to be negative b, which is r sub I, plus or minus, and we'll have to think about the interpretation of the plus or minus in a second, but plus or minus square root of the b coefficient squared, so that's r sub I squared, minus 4 times a times c, all over 2 times a. So 2 times a is just m. Okay, let's see what that looks like in Desmos. So here I've shown both the positive branch and the negative branch. Clearly, well, so let's talk about what the axes are here. So the x-axis is the total amount of work needing done, and the y-axis is the time that it takes. So clearly, it doesn't make sense to have the job take a negative amount of time. And like, actually, let's restrict this so that the amount of work done is positive. Oops. Okay. So this branch clearly doesn't make any sense. Which one was it? Is it that branch? Okay. So here we go. As the amount of work done that needs doing goes up, we have a root family which describes the total amount of time it's going to take. And by contrast, I've put back in the original model that has no fatigue, so the amount of work divided by the group rate of doing work. And so you can kind of see the difference between the fatigue model and the non-fatigue model.